So with a phase diagram, you will be able to get some information about the state of a substance at specific temperatures and pressures. You can see an example phase diagram down here. And the reason why temperature and pressure are included as the x-axis and the y-axis respectively are because there are two ways to cause a phase change. That is another way to say state change as well, aka turning something from solid to liquid or liquid to gas or so on and so forth. The way that we can do that we can change the state of a substance, is either by changing the temperature or the pressure. Having a high pressure, of course, means that we're exerting, there's a lot of particles being pushed together, which will allow for intermolecular forces to be strengthened, whereas a low pressure means that molecules have fewer collisions and will not have as strong of IMFs. So if you think about that just conceptually, a high pressure, if there's high pressure on something, you can think about things being pushed together. You're pushing together pieces, particles more strongly. It's going to allow for you to push those particles much more closely together. If you think about this in terms of a solid, you can see up here as the pressure rises, you can see that amount of area that this solid state covers increases, because even if the temperature is staying the exact same, if the pressure is increasing, then you are pushing those particles a lot closer together. Okay. A low pressure, of course, means molecules will have fewer collisions. They are not being as strongly pushed together, and so they're not going to be quite so densely packed together. The other way, of course, that we can cause a phase change is via a temperature change. A high temperature means that there is a lot of energy and movement associated with those particles. So if there's a lot of movement to the particles, there's a lot of kinetic energy to those particles, then that is going to allow them to kind of pull apart from each other almost. We're going to see the weakening of IMFs as these particles gain energy, while low temperatures mean less movement and intermolecular forces are strengthened as a result. They're not going to have as great of a tendency to kind of pull apart from one another. They don't have as much energy. So we can use this phase diagram that you see down here. This is just a generic phase diagram, by the way, not for any one specific substance. A phase diagram is a diagram that shows the different combinations of temperature and pressure that would result in a state of a substance, okay? So I want you to notice where the solid, the liquid, and the gas are positioned, okay? Solid is always going to be this segment to the far left. Liquid is always going to be kind of this weird, it's in between this, almost this fork in the line. And then gas is always going to be the area that is closest to the x-axis, okay? So there's your gas, your liquid, and your solid, your three states that we are concerned about in this class. And because of the different strengths of intermolecular forces in different substances, each substance has its own unique phase diagram. So carbon dioxide, for example, will have a unique phase diagram. Water will have a unique phase diagram. Bromine would have a unique phase diagram, so on and so forth, okay? And so right here on the temperature and pressure, if we were to line up this temperature with this pressure, we would be a gas, we'd be a liquid somewhere in here, and we would be a solid somewhere in here, okay? Those different combinations of temperature and pressure, we say, result in different states or phases of matter. As conditions change, as temperature or pressure changes, a substance may transition from one state to another, resulting in a phase change. So crossing the line like this is known as a phase change, and you can see some of them written in. Actually, all of them are written in. You have going from a gas to a liquid, you are told, is condensation. Going from a liquid to a gas is vaporization. solid to a liquid, melting, liquid to a solid, freezing, solid to a gas, sublimation, and gas to a solid, deposition. If conditions place a substance on the line, so at any point along this, if you're on the line, that means that both states are present at that time, and there is a phase equilibrium occurring between two phase changes. Okay, on the line, both states are present. So, for example, if I was like right here, there would be a phase equilibrium between liquid and gas. Phase equilibrium is a fancy way of saying that opposite phase changes occur at an equal rate. Opposite phase changes occur at an equal rate. So if you had, for example, a substance at this point, at this temperature and this pressure for like water, for example, there would be equal amounts of vaporization and condensation happening. That is a phase equilibrium. There is a special type of phase equilibrium that every phase diagram has called the triple point, which I'm going to star here. That there's the triple point. Our triple point is special because at this point, all phase changes and states coexist. All phase changes and states coexist. So you can have something that's like vaporizing and freezing at the same exact time. It's great. I'm going to actually show you a video showing the example triple point visual of tert-butyl alcohol. So I'm going to pause my recording so if somebody is watching this recording, they can pull up the YouTube video themselves and go see it. So hopefully that was interesting. So moving on down here, what I want y'all to do is take a look at this CO2 phase diagram. And you can see now, of course, we have some labels for temperature and pressure on the x-axis and the y-axis now, since this is specific for the CO2 substance, carbon dioxide. We have some questions that go along with this. We have letter A, for example, asking us if a sample of CO2 has a temperature of negative 100 degrees Celsius and a pressure of 100 atmosphere, what state is that sample in? So this is a case of you just finding the values and lining them up. You have a temperature of negative 100 degrees Celsius and a pressure of 100 atmospheres. So if you look on your diagram, that is right here. So what state are we at those specific conditions? Solid. Very good. We are solid. And letters B and C ask you to identify what phase change has been made when the following changes occur. So I want y'all to go ahead and look at letter B and C. Letter B, if you decrease the pressure to 0.01 atmosphere, so be careful, make sure you're looking at exactly the atmosphere value. This one is, we're going to get over here. So tell me what phase change occurs when we do this for letter B, and then try and figure out the phase change for letter C as well. I won't draw that one in. I'll let y'all try and draw that one in. And then we'll go over it here in a second. Okay, so can somebody maybe raise their hand and tell me what they think that B, what that phase change is? Solid to gas, I heard it. Yes, sublimation, very good. It is sublimation. If you go from solid to gas, that is sublimation. I'll tell you a way that I remember the difference between sublimation and deposition here in a second. But solid to gas, sublimation. And the other one We increase the temperature to negative 20 degrees Celsius, so... Melting. Very good, y'all. Melting. So that is solid to liquid. Hopefully y'all were able to see, if we go across this line here, that is getting us from solid to liquid. That is indeed melting. What questions do you have there? Okay, I'm going to tell y'all my quick way of remembering deposition from sublimation. So deposition is a process, sediment deposition is a process in like rivers, for example, when, you know, you have a bunch of sediments like floating in the water, right? And eventually they all, you know, deposition happens and they all kind of like settle. And so imagine, you know, all the sediments settling together. And if you think about that, if you think about, you know, sediment deposition or something like that, this is what I do. I think about all those particles coming together to settle together, and when they do that, they are much more closely packed together, which looks a lot like what a particle diagram looks like for a solid. So solids have particles that are fairly closely packed together. And if you remember that, then hopefully you can remember deposition, and then remember that sublimation is the other one. So, if you have a different way of remembering it, please let me know, because I would love to have another memory device to share with people. That's how I remember it. So, if we don't have any more questions about this page, we're going to go ahead and flip to page 14 and talk about heating and cooling curves. Heating and cooling curves. This is going to take up the bulk of our notes today, the heating and cooling curve. I want to make sure that we really understand what is going on in this diagram, and we're able to, you know, talk through it and draw ourselves our own heating and cooling curves as we solve problems today. So while our phase changes and our, you know, phase change diagrams, phase changes can be achieved by changing either temperature or pressure, the more commonly used method of causing a phase change is going to be the changing of temperature. Most of the time, pressure is typically constant for an area. You know, if you're at sea level, for example, the pressure's going to be pretty constant. And so the thing that's going to fluctuate is temperature, and this is a lot more easy for us to control if we're trying to cause a phase change. So when we are changing temperature, obviously we are going to alter heat or thermal energy, if you want to be specific about it. We're going to change or alter heat, but a change in heat does not always change temperature, which is what we are going to see in this diagram. Do y'all remember what temperature is a measure of? Kinetic energy, absolutely. So this is going to be a measure of average kinetic energy. Temperature is a measure of average kinetic energy. But if we are adding heat or thermal energy and it goes to something that is not thermal energy, it's going to something besides thermal energy, besides kinetic energy, then that temperature is not going to increase as a result. If we're putting that thermal energy towards the kinetic energy to raising the kinetic energy, then we'll see a temperature increase. But if the heat or the thermal energy is not going to kinetic energy, we are not going to see a temperature increase. This is the exact scenario that happens during a phase change. So what we're going to do is we're going to look at a heating-cooling curve so you can see this in context. I want you to go ahead and label your y-axis temperature, which we usually measure in degrees Celsius. You can also sometimes see it in Kelvin. And then I want you to label your x-axis heat added. So hopefully you can already see on this diagram there are certain parts of this curve where heat is being added but temperature is not increasing. The places where temperature is not decreasing but heat is being added are our phase changes. So let's look at the states that we have illustrated in these three positions here on our diagram. This first one with the particles packed very, very closely together, what state is that representing? Solid, very good. What about this middle one with them a little bit more loosely arranged? So we can melt to get from a solid to a what? Liquid, very good. And then the last state that we're representing here by the spread out particles, gas, very good. So, like y'all said, we're going to be able to go from solid to liquid by melting. What's the opposite? What's going from a liquid to a solid? Freezing, very good. And then what about going from a liquid to a gas? Vaporization. And then the opposite, going from a gas to a liquid. Condensation. You're going to condense. Condensation. So those are our phase changes along those flat, plateaued lines there. And so on our diagram as well, I would like to include in two little marks where those horizontal lines are. We have a special name for the temperature that constitutes this phase change here. What's this point, y'all? So this is the temperature at which this liquid freezes or this solid melts. So we call this the something point. The melting point, yeah. It's not really a trick question. The melting or the freezing point. So melting and freezing point are referring to the same temperature because it's the temperature that a substance melts or freezes depending on whether you're putting in energy or taking energy out. Yeah, if something had a freezing point that was like above our body temperature, then it wouldn't feel cold to us, which certain metals do. Yeah, like there's metals can be in like a liquid state or they can be in a solid state. And so if that metal's freezing point, I mean, there's certain things that are like solid in the solid state. There's metals in the solid state that do feel warm to us because they are at a higher temperature than our bodies. Yes. So it's kind of weird to think about, but yes. Some things have frozen, but they feel warm to us. Water, though, is something that freezes at a temperature lower than our body temperature, and so that feels cold to us. That's why ice feels cold to us. It's a good question. So, with that being our melting, our freezing point, the other one would then be the what point, y'all? The boiling point. Very good. That is the boiling point. Oh no, not my lights again. Always. Okay. It's just a routine procedure here. Okay, so our diagram here, what we have is, of course, heat or thermal energy being added if we are traveling up along this curve. And if we're traveling down this curve, we are removing energy, okay? So what I also want you to draw here is, if we're moving down the curve versus up the curve, we're going to have an exo versus endothermic process. If we are moving up the curve here, this would be an endothermic process. An endothermic process, a positive delta H. To get from a solid to a liquid, I have to put in energy, that's endo, to get from this state to this state, and then I have to put in even more energy to get from liquid to gas. And then the opposite direction is our exothermic processes. To go from gas to a liquid, there's actually energy being released to the environment. That is an exothermic process. a negative delta H. And so with our diagram labeled, I want to talk a little bit more about what these flat portions of the graph mean for us here. So that's where we're going to fill in some blanks down here. It says, notice that during a phase change, the temperature, what's happening to the temperature during a phase change, y'all? It stays the same. It does. It's not going up or down, like it's not traveling on a diagonal like this. During a phase change, the temperature is constant. It stays the same. This is a very important concept. I'm going to highlight it, so if you want to do the same or star it or something. But during a phase change, the temperature stays the same. The reason for this is because the heat changes, the energy we're putting in, are going towards changing the potential energy, an increase or a decrease, depending on, where we're traveling, what phase change is happening. The energy changes, the heat changes are going towards changing the potential energy in the form of weakening or strengthening IMFs. So we're going to change potential energy in the form of weakening or strengthening the IMF. For example, if you are looking at a heat change, a phase change, from liquid to gas, you're going from this liquid, this point right here to right here, liquid to gas, the temperature does not change during this phase change because the heat energy applied is being used to break IMFs, intermolecular forces. That is a potential energy change. So I want to show you what I mean by that. We're not making the molecules go any faster. Okay, we're not increasing the kinetic energy. We are just using that energy to break intermolecular forces. So think about a substance like water, okay? You have a bunch of water molecules hanging out together. Okay, and we have a bunch of water molecules hanging out together. The energy going from liquid to gas when they're, much more further spread out, like this, it's going towards pushing these molecules apart. Okay? I'm going to push these guys apart. This is a hydrogen bond. Remember that water, for example, the partially positive end of one water molecule is attracted to the partially negative end of another water molecule. So there's like a hydrogen bond happening there. So it's not a covalent bond. It's not a strong bond, but it is a force. There's an intermolecular force here. And in order to break that force, in order to break that IMF, we're going to have to put in some energy to push them apart, okay? About pushing them apart. It's going to take energy to do that. And as we do that, we're not actually making the molecules go any faster. We're just causing them to be spread further apart in the case of a liquid to a gas. Okay, you could go the opposite direction. You could condense and get these particles in gas form to go back to liquid form. But in doing so, they're not actually getting any slower. The temperature is not decreasing. There's just a little bit of energy release as those IMFs essentially kind of snap back into place. Remember, takes to break, freeze to form. It's kind of the same thing with our IMFs, in addition to when we talk about chemical reactions. So, in a phase change, all we're doing is breaking or forming IMFs, depending on which phase change is happening. We're not actually doing a chemical change here. We're just breaking or reforming IMFs, depending on the phase change. So with that knowledge, knowing that the temperature is not changing because that thermal energy, that input, is going towards potential energy changes, and the temperature, therefore, is not increasing or decreasing, I want you to remember the 3 P's of heating curves. We have 3 words that start with a P. We have plateau. The plateaus on the graph. The plateaus are our horizontal lines. The plateaus, are the 2 horizontal lines on the graph, are phase changes. And phase changes are where the potential energy is changing. So plateau, phase, and potential all start with P. Plateaus on the graph indicate phase changes, which are potential energy changes. What questions do we have there? Okay. Then I want to go ahead and talk about how we can do some math and how the math is going to be slightly different depending on whether or not a temperature change is happening or a phase change is happening. So the first thing I want to do is I want to point out what we've been doing up to this point. We have dealt with some temperature changes before. We did some temperature change problems when we were looking at calorimetry. We used this handy-dandy delta H equals MC delta T to calculate heat changes. And we can continue to do that so long as there is a temperature change. If you are trying to do a calculation for steps that involve temperature changes, aka the diagonals on the graph, you can use this equation. As long as your delta T is set up right, final minus initial, you should be able to get the correct sign. The formula will come out with the correct sign, positive or negative, depending on whether or not energy is released or energy is absorbed. So I want to come back up here, and I want to highlight all of my diagonals in green, just like I highlighted the MCAT equation. I can use the MCAT equation to calculate heat change if the temperature is changing. In other words, if I am on a diagonal on my graph. If temperature is not changing, if the substance is undergoing a phase change, then we have to do a little bit different. We have to have a little bit different approach. Okay? So for calculations that involve changes of state, phase changes, the flats of the graph, we're going to have to use this or this, depending on whether or not we're changing between solid and liquid or liquid and vapor states. So I'm going to go up and I'm going to highlight in pink my plateaus. These are where we would use this other approach. When temperature is not changing, we cannot use MCAT because there's a whole part of the MCAT formula that is delta T. There's no delta T here. It would be 0. You would get a 0, but there is heat change happening. So you have to be able to differentiate between the two. It's also important to be able to tell, am I going between a solid and liquid state, or am I going between a liquid and vapor state, and vice versa, okay? If you are looking at a change between a solid and liquid state, aka a freezing or a melting phase change, you are going to have to use something called the heat of fusion. This is delta H subscript FUS, heat of fusion. Heat of fusion, This is the amount of energy required to loosen the IMFs of 1 mole or gram of a substance between solid and liquid state. So notice how this is just like loosening IMFs. That's where all that added thermal energy or thermal energy that's being taken out, where what is accounting for that is the loosening or the strengthening of IMFs. So if you're going from solid to liquid, this is energy required to loosen, to get them out of this solid state and to get our particles a little bit more free-flowy, like we see in liquids at the particle level. Whereas going between a liquid and vapor state, aka going between liquid and gas, if you're going from a liquid to a gas, the heat of vaporization, as this is called, when you're going from a liquid to a gas, for example, the heat of vaporization is the energy required to break the IMFs. Both of these values, the heat of fusion and the heat of vaporization, can be stated as kilojoules per mole or joules per gram. All you want to do is just really make sure that you're paying attention to your units, because you need everything to be in the correct unit so that everything cancels out. Okay? And one more thing I wanted to point out before we flip to the next page. If you're ever asked to do a problem like this where you need the heat of fusion or heat of vaporization for water, that is a value that you have on your periodic table under our constants and conversions. You'll see the heat of fusion of water and the heat of vaporization of water. If you were asked for something else like liquid bromine or something and you needed the heat of fusion, they would give that to you. Or the heat of vaporization, they would give that to you. But waters is always on your periodic table, so they may not give that to you. I also want to point out that if you look here at water, the heat of vaporization is greater than the heat of fusion. That makes sense because, again, we said that heat of vaporization is the energy required to break the IMFs, whereas heat of fusion is just the amount of energy required to loosen the IMFs. So it takes more energy to break than it does to just kind of loosen those intermolecular forces. So just something I wanted to point out before we flip to the next page. What questions do we have before we get into some more math? Okay, then go ahead and flip to page 15. We should be on page 15 now. The last little thing before we do get into the math is just talking about these formulas that we just discussed over here on this page. Just an FYI, those two formulas, since there's not like a temperature final minus temperature initial part that you plug in, these formulas will specifically require you to pick a sign, positive or negative, depending on if the process is going to involve a loss or a gain of heat. So for these specific problems for phase changes, you are going to actually have to think about if the phase change is endo or exothermic, which is why I went ahead and drew these arrows showing you that going from this way, this direction to this direction is representing exothermic processes, whereas going from the solid to liquid to gas direction is an endothermic process. But I think that these kind of make sense if you kind of think your way through it. A lot of this unit is really helped by you being able to conceptually think through things. If you're thinking about getting your substance from a solid to a liquid and then a liquid to a gas, remember that I said it takes energy. We have to put in energy in order to push those little liquid particles apart to get to the gas. If you can remember just that little bit, that should help you remember that this is an endothermic process going up this heating curve. Because if you have to put in energy to break some IMFs, putting in energy is the definition of an endothermic process. Okay? So just be cognizant of the fact that you're going to have to look at the endo versus exothermic nature of that phase change. Okay? And then that was just what I just talked about with the vaporization versus fusion values. And then the other hint that we're going to look at as we get into these problems, as you approach any of these problems, make sure before you start doing calculations, before you start writing equations down, that you determine if a temperature change occurred or not. If they are giving you two temperatures a lot of times, that's indicating a temperature change. Whereas if they are telling you that something is vaporizing or melting or sublimating or something of that nature, that is a phase change. Okay, if we use our phase change vocabulary, like in our first example for lack of a better word, example. In this example, we are told to calculate the heat change needed to vaporize 346 grams of water. So, is that a temperature change or is that a phase change, y'all? Phase change. How can you tell? The word vaporize. Exactly. It is a phase change. We are specifically told that the water is vaporizing. So I'm going to write just a little note off to the side. You can too if you want to use this to study later. This is a phase change. If we're vaporizing, from what state are we going? Are we changing from to what state are we going to? Liquid to gas. This is a phase change from liquid to gas. And if it is a phase change, heat of vaporization, as a reminder, we're going to have to use one of our pink equations. Vaporization, right here, moles or grams times our heat of vaporization. What's nice about this is we can come over to our formula chart. Like I said, they will give you the heat of vaporization and fusion of water. Since we're going from liquid to gas, we're vaporizing something. That should clue you in to the fact that we're going to need our delta H of vaporization, our heat of vaporization, which we are told is 2260 joules per gram. So what this is saying is that I need 2,260 joules of energy to vaporize 1 gram of water. So I could set this up as dimensional analysis so I don't get lost. It's a simple one-step dimensional analysis. I have my starting value, 346 grams of water. 346 grams of water. And I know to vaporize 1 gram of water, this is this many joules per 1 gram, I need to put in 2,260 joules worth of energy. So simple one-step dimensional analysis. Go ahead and get your calculators out. Do that. What are we getting, y'all? Or I guess I should ask, how many sig figs should this be in? 3. Very good. I'm glad y'all clocked that's 3 sig figs. Okay. So you could put this in standard notation or scientific notation. Some of you might have an easier time rounding to 3 sig figs if it's in scientific. Somebody like to share what they got? Yes? Yes. 782,000. Or if you put it in scientific notation, you could do this as well. The last thing we need to do, I guess I boxed this before I did my sign, but the last thing we need to do is determine whether or not this needs a positive or a negative sign. So if we are vaporizing water, positive. Why do we say positive? Because it's what? It's going up the curve. Yeah, we said, things that if we're going up the curve this direction, we're going to have positive. If you want to think about it conceptually, think about the fact that we're going to have to put in energy, aka endothermic. Remember, endo, put in. We're going to have to put in energy to push those molecules apart. That is an endothermic process. Very good. So if you left the plus sign off, we would just assume that it was a plus sign because that's how numbers work. But if it was negative, we would need the negative or it would be wrong. Okay. Any questions there? Okay. And let's look at this next example, and then we'll do our big, longer example, and then do some other practice on our own, and I'll let you check your work with my key. So the second example asks us to calculate the energy change when 1.044 kilograms of water is cooled from 98.6 degrees Celsius to 32.3 degrees Celsius. Just looking at this problem, I want us to decide, is this a temperature change or is this a phase change? Temperature change. What's the giveaway there, y'all? There are two temperatures. Exactly. We've got two temperatures here. So this is specifically we're cooling. This is a temp change. I'm going to zoom in a little bit more since it's kind of hard to see my small writing. This is a temp change. No phase change. Okay. And so which one is our initial temperature, y'all? 98.6, and that would leave this one as our final. So I always like to label my initial and my final because as long as I write my initial and final correctly, aka final minus initial, and my, delta T is final minus initial. As long as I write that correctly, it should give me the correct sign, so I shouldn't have to worry about, thinking through whether or not this process is exo or endo. But we are cooling here, so if we are water at these temperatures, what state is water in between 0 and 100 degrees Celsius, y'all? Liquid, yeah. Between 0 and 100 degrees Celsius, water is liquid. Perfect. So we are cooling in the liquid state. So that's important to know because we are going to have to go grab the specific heat of water, and it does depend on the state that water is in. And so since we're doing a temperature change, delta H equals MC delta T, I want y'all to attempt this problem, but be careful. I would highly suggest including your unit for each of these values so you make sure that everything is in the correct units. You're going to need this, your periodic table, to figure out your specific heat of water, and you may have to do a conversion somewhere. So do that, and then we will go over it. Let's go ahead and go over this. So we're calculating our delta H here. And what did y'all put in for the mass of the water? So, 1,044 grams. Yes, 1,044 grams. So this in grams is this value. Why did y'all convert this to grams? Because it was in kilograms? Why did we need it to not be in kilograms? To cancel out the gram on the bottom of the other one. Yes, the gram on the bottom of specifically the specific heat. So we have our specific heat of water from our liquid water. Remember, it depends on the state. So the specific heat of liquid water, we know, based on our formula chart, is 4.184 joules per grams times degrees Celsius. So we want to be able to cancel these units out, so we want to make sure that these units are the same. Good, good. And then y'all did a good job identifying your final and your initial temperature. And if you know that delta T is final minus initial, you can just plug these guys in. And as long as you do that correctly, then your numbers should come out with the correct sign at the end. So I'd go ahead and round this guy to about 3 sig figs. What did y'all get here? Negative. It's a little weird. Yeah, so this is one of those ones that you kind of have to bump up everything else because of the weird rounding case. So I'll put this in here, you know, there's your grams, time your specific heat, times your 32.3 minus 98.6. I'm putting those guys in parentheses. You should get this, okay? If you want to put it in scientific notation, okay? So the 9 would be rounded up, which would make this 8 round up to a 9 as well. So negative 2.90 times 10 to the 5 if you want it to be in 3 sig figs. Y'all see that? Negative 2.90 times 10 to the 5. And then what is our unit for that? Joules, yeah. This is joules. Very good. Okay. So, any questions there? Clarifications needed. Okay. Which is, oh, it's almost frozen there for a second. This next one is a 3-part problem. What's nice is that there's a combination of things going on here in terms of phase changes and temperature changes happening to this one substance. But this problem has broken it up quite nicely for us into parts A, B, and then using parts A and B to calculate the answer to part C. That is how a lot of your problems on your practice worksheet are structured as well. Some of the problems on your practice worksheet are not broken up in this way, and they just want you to know, hey, you're going to have to do a couple different steps to do this one problem. So I would know how to do it both ways. It appears both ways on your practice worksheet. It could appear, you know, either way on your assessment. So make sure you know how to do it both ways. What we are going to start off with these problems a lot of the times is being asked to sketch out a heating curve. And here we are asked to sketch out a heating curve for bromine using the information that its boiling point is 59 degrees and its melting point is -7 degrees, melting/freezing point. We're going to label both of our axes and include the values for the melting and boiling points on the graph. Whenever you are asked to draw a heating or cooling curve, you are going to draw the same, almost the same exact thing every single time. The only thing that is going to change is the boiling and melting point. So when you're asked to draw something like this, I want you to draw your X and your Y axis. I want you to label your axis as well. So the X-axis should be heat added. If you want to include a unit, it should be joules or kilojoules. It depends on the problem, joules or kilojoules. Heat added, and then temperature should be your Y-axis. I'm going to leave a little bit of space also off to the side so I can include some labels. Heat added and temperature as your axes. And then you're going to draw the same heating curve every single time, y'all. Don't add in your temperatures yet. Just draw 3 diagonals and 2 horizontal lines. Okay? Draw 3 diagonals and 2 horizontal lines every single time, y'all. That is a heating/cooling curve. The only thing that changes is the temperature based on the substance, because temperatures, different substances have different boiling and melting points. And if you look at the values, you'll see obviously the bigger temperature is going to go on top, up higher on the axis. That's where your boiling point hangs out. So you have 59 degrees Celsius, that's my unit here, and you have -7 right here. All you have to do, you draw the same thing every time. The only thing that changes is your melting and boiling point. And it is great to have a visual like this when you're doing a problem like this without it being broken up, because you can track the diagonals and the plateaus. so you know whether or not you need to use an MCAT or a heat of fusion / heat of vaporization value. Okay. Y'all with me so far? So with our heating curve for bromine included or drawn in, we're going to go ahead and move to this next part of the problem where it says to calculate the energy change. Okay, we want to know the energy change for 125 kilograms of liquid bromine when the temperature is changed from 55 degrees Celsius to -7 degrees Celsius. Okay, 55 degrees Celsius to -7 degrees Celsius. So I like to put this on my graph here. Just hopefully looking at this problem, you can see it's a temperature change. If you go and try and put this on your little graph, 55 is, somewhere in there, and then -7 is right here. It does not say anything about a phase change in the phrasing here. So we are not going to go past this point. We're not going to get into the phase change process here. We are just looking at the temperature change from 55 degrees Celsius to -7 degrees Celsius, which is on this diagonal, as temperature changes are. They're on diagonals. So we are looking at this point, what state are we in, y'all? Liquid, yes, we are. We are in the liquid state. This is what state, y'all, up here? This is gas, and then this is solid. So in the middle is liquid. So at this, we're going to calculate the heat change from liquid bromine at 55 degrees Celsius to liquid bromine at -7 degrees Celsius. Okay, that's what we're looking at here, is this little piece, if you want to see that visually. Since we are doing a temperature change, are we going to need to do MCAT, or are we going to need to do the vaporization / fusion thing? It is MCAT, yes. MCAT, temperature change. When it's temperature change, you need to be thinking MCAT. Delta H equals MC delta T. And they were so nice, they gave us the specific heat of liquid bromine, because that is not on your formula chart. Like I said, if you need a different specific heat, they will give it to you, or they will make you solve for it. So what are we looking at mass-wise here? What should our unit for mass be when we go to set up our problem, y'all? Grams. Why? Grams, because it's on the bottom of specific heat. Beautiful. I want to be in grams. Convert kilograms to grams. Convert kilograms to grams because of this. So what is 125 kilograms in grams, y'all? It's just that, right? 125 times 1,000. $125,000. So let's go ahead and plug these in. Again, I just like to include my units to make sure I'm doing what I need to do. My specific heat, of course. And then, is 55 the final or the initial temperature, y'all? Initial. We're going from 55 to our final of -7. So -7 minus 55 degrees Celsius. Go ahead and calculate that. You might want to put this guy in scientific notation. It's kind of big. Make sure you know how to type this in. Give y'all a couple more seconds. So hopefully y'all got this. That's it in scientific notation. If you got it in standard, that's fine too. About how many sig figs should we round this to, y'all? 3. 3's good. So I'm going to go ahead, make sure I include my negative sign so it's not wrong. I did do my final and my initial correctly, so this is negative. What does the negative mean again, y'all? Exothermic. Very good. So this is exothermic. We're releasing this much energy. And what's our unit for energy here? Joules. Very good. So y'all did something like this up above. What questions do you have about this one? Cool. And the next piece of this problem that we're going to do, it asks us to determine the energy change when that same amount of liquid bromine freezes at 7 degrees Celsius. So do we need another MCAT here, y'all? No, we do not. Because what is freezing, y'all? It's a phase change. Freezing is a phase change. So if our liquid bromine is frozen at negative 7 degrees Celsius, okay, that is this segment. That is this segment of our diagram. That is a phase change. Oops. What happened there? Weird. Okay. So there is our segment we're going to be looking at specifically. And we are told the heat of fusion of bromine as well, because this is not something we have on our formula chart. So determine the energy change when 125 kilograms of liquid bromine is frozen at this temperature. And we know that there's this many kilojoules going to be, or actually I guess I should ask y'all, if we are going down this line like so, is this an exothermic or an endothermic process? Exothermic. I mean, you already saw that obviously here we were going to have a negative value, so this is an exothermic process. So if we're looking at the heat of fusion of bromine when it's freezing, what this is telling me, and you want to write this down to help you remember this later, is that 10.57 kilojoules of energy needs to be released to freeze 1 mole of bromine. What? 10.57 kilojoules of energy needs to be released to freeze 1 mole of bromine. And what we can do here is we can do a little bit of dimensional analysis to figure out how much energy we need to release to freeze this much bromine. Okay, we know, we just did a conversion earlier, this is 125,000 grams of bromine. I'll use parentheses here for those of y'all who like to use parentheses. I know that I can go from grams of bromine to moles of bromine, and then using this as a conversion factor, I can go from moles of bromine to kilojoules released. So how many grams are in 1 mole of bromine, y'all? You're going to have to use your periodic table for that. 159.8. that many grams in 1 mole of bromine. And then we know that for every 1 mole of bromine, you have to release this much energy to freeze that mole. So calculate that. Make sure you include the correct sign. If you have determined that this is exothermic, make sure the sign is correct. Okay. For the sake of time, I'm going to go ahead and put the answer to this guy right here. That is how much energy is released in kilojoules. Remembering again that this is exothermic, so we do need a negative sign. Anyone still using what I have on this page? Cool. Then the next page, what I want you to do is look at this. This is asking us to determine the total energy change in kilojoules when all that stuff that we just calculated happens. So the total energy change in kilojoules when 125 kilograms liquid bromine at 55 degrees Celsius is changed to solid bromine at negative 7 degrees Celsius. So this whole piece going from here to make sure that it is frozen, we have to add these two pieces together, because that is the total amount of energy that needs to be released to first cool that bromine to negative 7 and then to freeze it at negative 7 degrees Celsius. So we're going to use our steps from B and C. When we cooled from 55 degrees Celsius to negative 7 degrees Celsius, when we did that, we released, I'm going to go ahead and convert, it was negative 1.78 times 10 to the 6 joules, which is in kilojoules, is negative 1.78 times 10 to the 3 kilojoules. So I'm just going to go ahead and put it in kilojoules. It's negative 1.78 times 10 to the 3 kilojoules plus our negative 8270 kilojoules. This was to freeze. I'll color code these guys. It was to cool and then to freeze. You add those guys together. You should get this, or negative 1.01 times 10 to the 4 kilojoules. Okay. So the amount of energy that needed to be released to cool it to this temperature, and then the amount of energy that needed to be released to freeze that amount. In total, to get from, point A to point C or whatever, is this value. Those two things added together. Make sure you preserve the sign. They are both negative, so they will make a larger negative number, like a negative number that is greater in magnitude. What questions do y'all have there? Okay. Then this next piece, I will post my key I'll try and post my key for the rest of this so y'all can check your work on Canvas. And just an FYI, this is one of those examples that is like this example we just did, except they didn't split it up into parts A, B, and C. I believe there's 3 different things you have to solve for here, 3 different steps, but it's not split up like it was for this problem. So just be aware, you might see some of those on your practice worksheet as well.